episode of my fantastic transistor testing here. This transistor that I'm having here is the most powerful transistor that I'm having in my arsenal. Look how beautiful outside is looking. Very beautiful. These transistors are the most powerful that I have in my arsenal. 150 watts, 23773. And here it is. This is how it's looking. And you can see the writing on it. And it's having this cool blue isolation here for the pins. Very cool. And here is the transistor, the testing transistor. I mounted it like this vertically for me to be easy to put my hands on it on one side and on the other. So to put my hands here on this side and here on this side. So as you can see, it is here on this surface is this radiator, aluminum radiator that I mounted it here. So I put two holes for the pins, and the pins are dangling exactly in the middle of those holes, very carefully, of course. Yeah. Let's see if I can zoom in. You can see some shit. Yeah, you probably can see the transistor that is inside. Okay, and two screws to mount the transistor there, and that's it. And I took already some measurements, and I reached at this fantastic wattage of 5 watts. Yay! But in my limits, in my 49 degrees Celsius, which is a little bit less, which is in the limit of 50 or less than 50 degrees Celsius. So I'm very, very happy with let me explain to you what I did here. My ambient temperature is 26 degrees, a little bit higher than 25 that I'm usually I'm having it here. This is the voltage, and as you can see, this column is 5 all the time is constant, and only the amperage is changed by turning this knob here, and then by looking there. You see, so here on the top is the voltage, and here is the amperage, and right now it's 5 volts and 1 amp, and is exactly what I'm having here noted, 5 volts and 1 amp. And here is the wattage that I calculated for everything. In the beginning I left it with this tolerance margin, but then I just by the way, this total power and amperage is for the entire circuit, including the wires, everything that you are seeing here, from here to here, including that, and including this resistor and that circuit. But they are consuming a minimum wattage dissipated on them. The biggest fall of wattage is over the transistor. So maybe it's not exactly 5 watts, is maybe probably 4.8 or something, very, very close to this number. But the big bulk of wattage is over this transistor, pretty much. And the temperature, I took it again with my temperature tester that I'm having it from eBay. It's reasonable. This is the probe, which I don't like at all, because it's very flimsy and is prone to break at some point because I'm pressing it sometimes without thinking. So 27, but it was a little bit more colder probably right now. My room got heated up by this transistor. So it's not 26 right now, but it was when I started everything. So this is how I'm doing. I'm keeping the temperature probe in my hand, and I'm going on this side here, and I'm touching there, very close between, well, on this radiator pretty much, and I'm looking here. So it's 50 right now, it's 51. But usually all this data that I took, I was a little bit impatient, and I waited like 3 minutes, maybe 5 minutes, but I doubt it. Somewhere around 3 minutes, I was waiting a little bit, to gather this final temperature. But usually it will rise up a little bit more than it is here, like with a couple degrees. So now, yes, this is not right. 56 now. Yeah, well, 7, 50, 60. Oh. Not good. But it is relatively tolerable, this higher temperature, because I leave it a little bit more longer than 3 minutes that I took the tests for. So it's 10 degrees over my 3 minutes here. This is 3 minutes, and so plus 10 after, I'm not sure, after 10 minutes probably, or around 10 minutes of, and usually it will reach a point of stabilization, total stabilization, and that's with time, and I don't have time to stay and test it rigorously, but I'm quite happy, I guess, with this size of radiator that is made from multiple, as you can see, there are 1, 2, 3, 4, I have 4 bands or pieces that I cut. Illumination stand, and it was from aluminum, the border, it was like a border all around, and this is scrapped aluminum pretty much, and it was painted with a white paint, and I had to find a way to remove that paint. And one day I stay and removed everything and clean it up, and then with this kind of abrasive paper, I'm not sure, grit. It's having like 200 like that, somewhere there, 200 grit, abrasive paper, and I clean it up, and it took me one day to prepare all these 4 motherfuckers that you are seeing here, and today I started to drill the holes, to calculate, to fit everything correctly, and it is dissipating the heat relatively conveniently. But for 150 watts, right now I'm at 5 watts, and it's already 60 degrees Celsius. Let me take the temperature again, because I closed it. Let's see what it's saying. Yeah, 26, you see, 26. And now it's raising because probably it's sensing my my hand temperature. So let's see now. I swear to God, probably it got more heated in the room from this guy. I know it's funny. So now I'm touching again there, around him, you know, near him, very, very near. So now I'm at the 50 there. No, 60. Very quickly it got to 60 actually. And it's running for, yeah, about 10 minutes, more than 10 minutes. 62 even, yeah. Plus 10 degrees. So you have to keep in mind to add, if you are making some tests, some quick tests of 3 minutes or so, you have to keep in mind to add another 10 degrees for more duration of time if you want it more permanent setup that, you know, like I'm having it here. Yeah, 58, 59. Depends when I'm moving this probe around. Yeah, 62 even. That's not cool. But it's good enough. And if I'm touching it with my finger, yeah, it's very hot, very, very hot. It's blistering hot. I can touch it a little bit, but no, not keeping it there because it's quite hot. All right, so this is my test. By the way, this is cold, absolutely cold. It's having no issues. I wish my transistor would be so cold like this. And like my friend was saying, 50, not 5, 50 watts, and barely is reaching. Yeah, unfortunately. But it's I suppose it's good enough for 5 watts. I suppose yeah, it's good enough from the tests that I did last time. But I used a very large heatsink. This is yeah. I'm having problem with materials. I don't have materials, and this kind of transistor I cannot actually mount it on this kind of aluminum heatsink because I really need to put this face over that flat face. So I really need to drill it, and I don't want to mess it up because this is quite expensive actually. Problems if I will have problems with my computer sometimes, and it's good to have a second radiator in storage. I really hope I can put my hands on a very thick bar of aluminum or even copper. Copper will be even better than aluminum. It will conduct a little bit more faster the heat, and it will dissipate more faster than this. It will be more cooler theoretically. I can add a fan to blow air on it. That's another idea to increase the wattage with this size of the heatsink that I'm having here. Yeah, and it's quite thick, believe me. Let me actually show you with my ruler how thick this entire thing is. So I'm having here is inch for my American friends. So it's from 0, 1, 2, 3, 0, 3 inch, 0.3 inch probably. 0.3 inch. I am not completely sure how to read that. I'm not American. This is 5 millimeter. So 5 millimeter is like that. 5 millimeter in thickness here. You can see. Yeah. And it's quite, of course, it's having points of contact, not flat contact, but it is dissipating quite good. Very good actually, all the heat on everything here, and it's good that it's having some air gaps. These things are a little bit bent like that, and in some points are making very strong contact, but not everywhere. So it's kind of like this, where it's having a little bit of air gaps, which is good. In the middle is very pressed, but in the margin are like this, you know. So yeah, I really need a very large, like my fist, like 2 fists, 1 and 2, to actually make a real proper experiment. Believe that I will get very close to the datasheet specifications, especially for this transistor. So I will get very close to this 150 watts that you are seeing here. You see 150 watts. If I will have a stupid big, like a lingo, like a brick of aluminum, or even copper. Copper will be even awesome to have, even more awesome to have. Yeah, making exception that, but is the biggest aluminum heatsink that I used probably so far, even bigger than this. And probably I'm not completely sure, but this I could drill it. That's the difference. This I didn't want to drill it, and I find this scrap aluminum, and yeah, it got loose here. But it's good that it's not powered anymore. Right now I close it. So yeah, it's a little bit disappointing because the size of the heatsink must be very big, and also it is becoming heavier with all this aluminum. It's metal, and we all know that aluminum is lighter usually, but it's still having some weight on it, and it's getting a little bit heavier, the entire ensemble. Yeah, but imagine when you will have when I will have a brick of like this height and this wide and long like this, like super, you know, like a brick, like I'm saying it, you know, and that will be a very decisive element to test. Then I will be happy to actually test this. Every transistor that I'm having, actually, they should go in that size of heatsink. That's my opinion. All right, that's it for this test. I wanted to push it up a little bit from its standard, from its naked, in the breeze, in the air, in the wind test that I did last time. So if you remember last time, it was staying by itself without any kind of heatsink. So now is a little bit of heatsink that I managed to scrap and to drill it to actually make it fit there. So yeah. Now it's unfortunate that this got loose. You will think it was like this all the time, but it wasn't. It's not because of the heat, but I probably tremble it, and yeah. Unfortunately, I don't have the proper transistors. If they are better constructed transistor inside with bigger dies, better material that is used in that die to to disperse the heat more efficiently, or to resist to more amperage, to more power, basically. So the composition inside the transistor to be like that. If they exist in this world, I never hold one in my hands ever. So I don't know if they are actually in existence, such very powerful and very good transistors. So far, what I tested are these commercial transistors that everybody can find. I will not say they are crap transistors or they are bad, because they are all that I know and all that I used. And I actually made a little bit of expense. I got in the woods with the money buying these guys here, that I'm not sure what I will use for making abstraction of this experiment that I use here, but I was very curious if they will resist better than my, and they are comparative with this. They are a little bit better, but well, I really need a bigger heatsink, because it's not a good comparison. Last time I reached like 19 watts with this guy, but it was on this very extremely good heatsink that I'm having here, and here this is a crappy, more crappy heatsink. So it's not a good comparison between the two, but it is more powerful. It's obvious more powerful, this transistor that I'm having here, than that guy. So it's better, it's way better, way more better, this one to use for more power circuits in general, to drive more power through them, through this transistors. It's an interesting thing. In time I will find a very good usage of them, but in time, in the future. All right, thank you very much for watching, thank you very much for listening. Also leave a like, and see you later on the next episode. Bye bye from your favorite artist, electronics, Mr. Q12. Bye bye.